we now consider some of those considerations that led to the general theory of relativity. First, we discuss the principle of equivalence. The non-relativistic theory of motion under gravity involves two laws. The first one is how a material particle moves under the influence of an external force, and that is given by Newton's second law of motion, which reads the acceleration A equal to the force vector divided by mi, where this constant factor mi of a particular material particle is called its inertial mass. F is the total force acting on the particle, and A is the rate of change of velocity of the particle, or we may also write A equal to d square r by dt square, where r is the position vector of the particle. Now, the second part of the theory of gravity involves the origin of this force because of the presence of material particles. And that is given by the Newton's law of gravitation, which says that the massive particles attract each other. In terms of the gravitational fields, one would say that matter produces a gravitational field, say denoted by the symbol phi of r. And if a point particle is placed in the gravitational field, then the force acting on it is proportional to the negative gradient of this gravitational potential field, and the proportionality factor will be called the gravitational mass of the particle. So the matter produces a gravitational field, potential field phi, and if another material particle is placed in that field, it experiences a force which is proportional to minus gradient of this phi, and the proportionality factor is written as minus mg subscript g times gradient of phi, and this is called the gravitational mass of the particle. And thereby there were experiments by lots of people, and who found that the gravitational mass is equal to the inertial mass. If we look carefully at these equations 1.1 and 1.2, we see no relationship between the inertial mass mi and the gravitational mass mg. Their origin are different. One comes from Newton's second law of motion as a proportionality constant connecting the acceleration of the particle and the total force acting on it, and the second comes from the Newton's law of gravitation, which gives the total force acting on a material particle because of the gravitational field phi, and the proportionality factor there is called the gravitational mass. Now, experiment showed that the gravitational mass is equal to the inertial mass, and this has a profound consequence. For example, then from this first law of motion, the acceleration on a particle is given by F divided by mi, but if the particle is placed only in the gravitational field, the force is simply given by minus mg times gradient of phi divided by mi. Now, because of the equivalence of mg and mi, this means acceleration of the particle is given by minus gradient of phi. So we have a gravitational potential field phi, and the acceleration of any particle placed in that field is equal to minus gradient of phi. and this does not involve any factor of either mi or mg, which means any particle, irrespective of the mass, will satisfy the same equation of motion in the presence of gravitational field only. That is, there is no other force, only gravitational force is present, and in that case, for any particle, whatever be the mass of it, it satisfies the following differential equation: A, which is given by d square by dt square, is equal to minus of gradient of phi. Now this has a solution given an initial given proper initial conditions. So one has to specify the initial position and the initial velocity, then it will have a unique solution. And given those initial conditions, any particle with any mass will follow the same trajectory, because the solution will be the same provided the initial conditions are the same. So, irrespective of the mass of the particle, all material particles follow the same trajectory if the initial conditions are the same under gravity only. That is, there is no other force acting on the particle. And such trajectories are special, and they are the same for all particles. So, this cannot be, so this is something universal. So in that respect, the gravity force, the gravitational interaction is different from all other forces. For example, it is different from the electromagnetic or electrostatic force, because the acceleration due to an electrostatic force, for example, by an electric field on a charged particle, is given by A is equal to F by mi, and if it is a charged particle of charge q placed in an electric field E, F is equal to QE, then acceleration is QE divided by mi. Now as q changes, the charge changes, the acceleration will be different, and as mass changes, the acceleration will be different. So the gravitational force is fundamentally different from others because it is universal for all particles, irrespective of the mass of the particles. All of them satisfy the same equation if there is only gravitational force acting on them. All of them will follow the same trajectory provided the initial conditions were the same. And these trajectories are called inertial trajectories, or they are called freely falling trajectories. As a next step, we consider a particle experiencing no force viewed from a frame of reference S dash moving with an acceleration A with respect to the lab frame S. So we have a frame S and another frame of reference S dash, which is moving with an acceleration A, and the direction of A is given here. Now, the origin of the frame of reference S dash with respect to S is given by this position vector R in the frame S. Now consider a particle given by this black dot here, and its coordinate in the frame S is given by the position vector R, and its coordinate in the frame of reference S dash is given by the position vector R dash. Now this is pre-relativistic physics, and the transformation between frames of references are given by the Galilean transformations, and we can immediately see from this construction that R dash is related to small r and capital R via this vector equation r dash is equal to r minus from the triangle law of addition of vectors. So that is this equation. Now taking the derivative, so taking the derivative of this equation twice with respect to time, we will get d square r dash by dt dash square, because t dash is the same as t. So this is a non-relativistic theory, and therefore time flows universally. The time for frame S is the same as time for the frame S dash, provided the clocks used by these two frames of references are synchronized. So taking derivative with respect to time twice, I will have d square r dash by dt square. But since t is the same as t dash, I can also write this as t dash square equal to d square r by dt square on the right hand side minus d square capital R by dt square. So that is this equation. But now this capital R is the position vector of the frame of reference S dash in the frame S, and therefore d square r by dt dash square is the acceleration of the frame S dash in the frame, measured in the frame S. So we have d square r dash by dt dash square equal to d square r by dt square minus a, where a is the acceleration of the second frame. Now the force acting on the particle in the frame S dash will be equal to the product of its mass times its acceleration. So that means we have m a dash, where a dash m times d square r dash by dt square, which we may write as f dash. So that is the force acting on the particle in the frame S dash, m times d square r dash by dt dash square, which is equal to m times, that is m times this is equal to m times d square r by dt square minus ma. So if I call this as f, the total force as seen by the particle in the frame F, and this is the total force as seen by the particle in the frame S dash, we see that f dash is equal to f minus ma. So that means in the second frame S dash, the particle, in addition to the force F that it experiences in the frame S, feels another additional force, which is given by minus m times a. So this is due to the acceleration of its frame of reference, and it is called a fictitious force. Now we consider a particle in a gravitational field, and we consider an infinitesimally small spatial region, and in which the gradient of the gravitational potential is the same, and we call it equal to g, the acceleration due to gravity. Since the spatial region is infinitesimally small, the gradient of phi do not vary much, and it is approximately a constant, and we can call it g. And if an observer makes observations of particles that are falling only under gravity, the free falling particles, he will not be able to identify whether the acceleration the particle is feeling is because of the gravitational force, or if this acceleration is due to his frame of reference, or the frame of reference of the particle having an acceleration exactly equal to minus g. So this is because in that region acceleration due to gravity is constant, g is constant, and therefore he will not be able to say whether this is because the frame of reference in which he is at rest is actually having an acceleration in a direction opposite to the acceleration due to gravity, or whether it is due to gravity. Of course, he will be able to say this once he make measurements by going to other points. But if he restricts himself to a small enough region of the space, then he will not be able to say for sure whether it is due to gravity or due to the acceleration of his own frame of reference. And this is because, whichever particle he uses to study the free falling motion, all of them will follow the same trajectory, which is the same in the case of the motion of a particle in an uniformly accelerated frame of reference here. For example, if the force F here is 0, then F dash is simply equal to minus ma. And if minus a is equal to g, I can write F dash as m times g. Now, whether he use different particles or not, and whatever be the mass of the particles he use, all of them will satisfy the same equation, and therefore he will not be able to say for sure whether it is due to gravity or due to a uniform acceleration of his frame of reference. If it was an electrostatic force, of course he will be able to say, because then he can use a charge. Say if initially he was studying motion of a charged particles with charge plus q, he could take another particle with charge minus q. Obviously then he will be able to say whether it is due to the electrostatic force or because of his frame of reference having an acceleration. Because if we use a different charge, then the acceleration of the particle will change. If he uses an opposite charge, then the direction of the force and direction of motion of the particle will change. The direction of the force will change. But if he is making observations only on freely falling particles, he will not be able to make a distinction between these two. That is, whether his frame of reference is having a uniform acceleration or whether he is in a gravitational field. And this observation led to the formulation of weak equivalence principle, which says that motion of a freely falling body are the same in a gravitational field and in a uniformly accelerated frame in small enough regions of space-time. And this is very important, that one has to restrict oneself to small enough regions of space-time. That is, the observer should make only observations, local observations. He could not, he should not go far from the point at which he is making observation. If he does that, he will see that the gravitational acceleration at different spatial points and at different times are different, and therefore he will be able to distinguish the gravity field from a uniformly accelerating frame, the effect of a uniformly accelerated frame. So, weak equivalence principle says that if one restricts oneself to the study of freely falling particles in small enough, that is infinitesimally small regions of space-time, then the observer will not be able to distinguish between the effect of a uniformly accelerated frame of reference and the effect of a gravitational field. So the basis of this is the equivalence of, or the equality of, the gravitational and inertial masses. But as special theory became known, special theory of relativity was proposed, a mass was no longer a frame independent quantity. It is coupled to the energy momentum, and therefore mass can be converted into energy, into different forms of energy. So if mass is coupled to different forms of energy, obviously we expect, and since we know that the weak equivalence principle comes from the fact that inertial mass is equal to or the same as the gravitational mass, and since now with the advent of special theory of relativity, the mass can couple to other forms of energy, we would now see that this weak equivalence principle can be extended to include other forces as well, other interactions as well, because this mass couples to other forms of energy as well. So then this idea leads to the strong equivalence principle and the Einstein equivalence principle, which we abbreviate as SEP and EEP. And the strong equivalence principle is stated in the following way. In small enough regions of space-time, it is impossible to distinguish between a uniformly accelerated frame and a frame in a gravitational field by any local experiments involving any law of physics, not just those involving freely falling particles. If we are only considering freely falling particles, we are allowing the particle to move only in the gravitational field and in no other field. So in that case, the equivalence of gravitational and inertial masses would imply that all particles will follow the same path, which we call the inertial or freely falling trajectories. But now, since mass is no longer a frame independent quantity and it couples to all forms of energy, the equivalence of inertial mass to gravitational mass would then be extended to the equivalence of this mass to any other form of energy as well, and therefore this would in turn imply that any law of physics or experiment involving any law of physics should not be able to distinguish the effect of a uniformly accelerated frame of reference and that of a gravitational field. If we are only performing local experiments, that is, experiments that involves only small enough regions of space-time. And the Einstein's equivalence principles say that in small enough regions of space-time, the laws of physics reduce to those of special relativity, and this is because of the following. In small enough regions of space-time, it is impossible to detect the existence of gravitational field by means of local experiments involving any law of physics. So that means there is no such thing as a gravitationally neutral object with respect to which we can measure the acceleration due to gravity. And because of that, one cannot actually consistently define an absolute acceleration due to gravity. And therefore, we have to abandon the idea of gravity as a force that produces an acceleration. Instead, we can have another idea, and that is the idea of inertial trajectories or freely falling trajectories. And these are the trajectories followed by material particles under the influence of gravity only, in the absence of other forces material particles follow the same trajectory. All material particles follow the same trajectory provided their initial conditions were the same. Now, if we consider a small enough region of space-time, we can attach inertial coordinates to a particular point in an inertial trajectory or a free-falling trajectory. However, an inertial coordinate system constructed in this way is valid only in an infinitesimally small region of space-time around that particular point. If we move away from this point, then we would see that the gravity, acceleration due to gravity at other points will be different, and therefore these coordinate system that we used will look like a curved coordinate system. But if we restrict ourselves to small enough regions, that is infinitesimally small region of space-time, we can construct inertial coordinates that will be valid only in that particular region. So the inertial coordinate system that is constructed this way, by attaching an inertial coordinate system similar to that of special theory of relativity that we considered earlier, at a particular point on a freely falling trajectory, will only be a local inertial coordinate system, because we cannot move away from this point and expect that the same local coordinate, inertial coordinate system describe other points as well. So if we restrict ourselves to small enough regions of space-time, we can have an inertial coordinate system that will appear almost representing a flat region of space, in which the law of physics can be expected to be the same as those of special theory of relativity. So this is embedded in the Einstein equivalence principle, which says that in small enough regions of space-time, the laws of physics reduce to those of special relativity. We will now discuss another principle that form one of the backbones of the relativity theory, called the principle of covariance. To demonstrate this, we first consider two frames in non-uniform relative motion. Consider a frame S and another frame, say S bar, where S bar is moving with relative acceleration a with respect to the frame S, and this acceleration is along the x-axis. And we also assume that at time t equal to 0 and t dash equal to 0, where t dash is a time measured, t bar equal to 0, where t bar is the time measured in the frame of reference S bar, and t is the time measured in the frame of reference S. And when t equal to 0 at equal to t bar, we assume that the two frames of reference coincide, and that the S dash frame start from the rest at t dash is equal to 0. Now, assuming that a is very small and t is also very small, so that the velocity of S dash is very small with respect to c compared to c, then we can use the approximation of the relativistic transformation equation, the Lorentz transformation, which is the same as the non-relativistic transformation. So Lorentz transformations in the limit of b by c much less than 1 reduces to the transformation of the non-relativistic theory. So we have x dash is equal to x bar equal to x minus half at square. That is because considering a particular event over here with coordinate say x in the frame S and x dash in the frame x bar in the frame S bar, we see that this distance from the origin of S to the origin of S bar is simply the distance traveled by S bar in time t. But that is given by, this distance is given by my half a t square. Now from this geometry we see that x is equal to x bar plus half a t square. Or in other words, x bar is equal to x minus half a t square, and that is this equation. Now y bar and z bar does not change. Similarly, t bar is also equal to t, because the t bar involves gamma factors of gamma, but v by c the whole square is much less than 1, and we neglect that in the non-relativistic limit. So the inverse transformation of this is given by x equal to x bar plus half a t square, which is obtained by taking this to the left side and noting that t is equal to t bar, so that this equation becomes x is equal to x bar plus half a t square, but t is t bar, and therefore this is equal to x bar plus half a t bar square. And this equation simply becomes y is equal to y bar, z is equal to z bar, and t is equal to t bar. Now the metric in the S frame is given by ds square equal to c square dt square minus dx square minus dy square minus dz square, which can be written using our using the notation involving the metric tensor earlier, can be given by eta mu nu dx mu dx nu, where we have used the convention x1 is x, x2 is y, x3 is equal to z, and x4 is equal to ct. And in that case, the components of the metric tensor eta is given by the diagonal matrix with diagonal elements minus 1, minus 1, minus 1, and 1. Now this metric or the interval element is expected to be invariant under this transformation, because it should be the same for all observers, an observer in a frame S bar and in the frame S. So that means in the frame S, assuming that the metric tensor is given by g mu nu, ds square should be given by g mu nu dx bar mu dx bar nu. But now this should be equal to this expression given by 4.2 as well. But that involves dx mu and dx bar nu. But we know how x mu is related to x bar mu, and therefore we know how dx bar mu is related to dx mu. We obtain that by taking the coordinate differentials from this equation 4.1. So we get dx1 is equal to dx, which is taking the differential of this form, this is equal to dx bar plus a t bar dt bar. So a t bar dt bar. So this is equal to, since dx bar is dx bar 1 and c t bar is equal to x bar 4, and similarly dt bar is equal to x bar, sorry, d x bar 4 by c, and t bar is equal to x bar 4 by c. We have a t bar dt bar equal to A times x bar 4 by C times dx bar 4 by C. So that is A by C square x bar 4 dx bar 4. We can do similar differentiation for dx2, dx3 and dx4, which is simply C times dt, which is dx bar. Then we can substitute for dx mu and dx nu, which is dx square, dy square, dz square and dt square in this equation. So we will get that equal to ds square equal to minus dx square, which is given in terms of the barred coordinate by this expression. So that is equal to minus of dx bar 1 square plus a square by c to the power 4, then x bar 4 square dx bar 4 square. Then the cross product, that is 2a by c square x bar 4 dx bar 1 dx bar. Then minus of dy square minus dz square, which is nothing but dx bar 2 square plus dx bar 3 square plus dx bar 4 square. But dx bar 4 is simply given by that. So dx 4 square, which is simply given by dx bar 4. So that is this. Now we group together similar terms. We look at terms involving dx bar 1 square, and there is only one term, that is this one, the first term. So that is written over here. Then we consider terms involving dx bar 2 square. So that is coming from here. Again, minus dx bar 2 square. And similarly dx3 square. So minus dx3 square. Then dx4 square. So it has two terms that involves dx bar x bar 4 square. And the first one is this. And the second one is this. So that is equal to dx bar 4 square times 1, then this comes with a minus sign, minus a square by c to the power 4 x bar 4 square. That is this. Then there is a cross term involving dx bar 1 and dx bar 4, and that is given by this factor of minus is there, minus 2a by c square x bar 4 dx bar 1 dx bar 4. But we already know that we already expect this to be of the form g mu nu dx bar mu dx bar nu. So comparing this with this, we see that there will be coefficients g11 corresponding to dx bar 1 square, and that is equal to minus 1. Similarly, g22 corresponding to this, that is also minus 1, dx3, which is g33, that correspond to dx bar 3 square, and that is also minus 1. Then there is g44, which correspond to the coefficient of dx bar 4 square, which is given by 1 minus a square by c to the power 4 x bar 4 the whole square. And then there is this cross term involving x1, x bar 1 and x bar 4. And since this metric tensor is taken to be symmetric, we can see that this is coming from two terms, that is g14, which is also equal to g41. So we will take g14 to be half of this and g41 to be half of that. So we will have g14 is equal to g41 equal to minus a by c square x bar to the power 4, and that is this. Sorry, not x bar to the power 4, minus a by c square x bar 4, the fourth component, the fourth coordinate, which is equal to c t bar. Now this metric tensor depends upon the coordinates, and also it involves a second order term in the coordinate. So that means there will be a non-zero second derivative for the metric tensor, and therefore the curvature tensor will be non-zero for this metric tensor. That means this new frame of reference, which is attached to S dash, which is moving with an acceleration a, correspond to a coordinate system or correspond to a space that is curved. So the space-time is curved in this case, whereas when we started originally with the frame of reference S, the interval that we have expressed over here corresponds to a flat space-time. So if we want to write the laws of physics in S and S bar, we see that in S, the laws of physics written will correspond to laws of physics written for a flat space-time, whereas in S bar, it will correspond to the laws of physics written in a curved space-time. Obviously, those two will not match. So this can be resolved by demanding that all laws of physics should be written in such a form that it should have the same form for all observers. And this requirement is called the principle of covariance, which says that laws of physics should have the same form for all observers. So we will only accept a particular statement of the physical law as valid only if it is a covariant, that is, it has the same form in all frames of reference. Obviously, such a statement of the physical law should be written as a tensor equation, and at best it can involve only the metric tensor corresponding to the space-time involved, metric tensor and its derivatives. So we have now discussed two important principles that will lead to the general theory of relativity. The first one is called the equivalence principle, which in the form of the Einstein's equivalence principle would say that the laws of physics should reduce to those of special relativity in small enough regions of space-time. And the second one is the principle of covariance, which demands that the laws of physics be formulated in the form of covariant equations. That means the laws of physics should have the same form for all observers. So in different frames of reference, they should have the same form, and therefore they should be written as tensor equations. We will now consider some of the consequences of these two principles. First, consider the consequences of principle of equivalence. The first example we consider is called the gravitational redshift. Consider a frame of reference which is moving with an acceleration a in this direction, and let S be a source of light and D be a detector of light. Both of these, S and D, are at rest in this frame of reference, and they are separated by a distance h. Now assume that S emits a photon with a frequency nu and D observes it. Let the time at which S emits a photon be t1, and in this frame of reference, light travels with a velocity c, and in any frame of reference, light travels with a velocity c, and therefore the time taken by the light photon to reach the detector is given by the distance divided by its speed. So that is given by h by c. Now by this time which is taken by the light photon to reach from S to D, so that is delta T is equal to h by c, the frame of reference would have achieved additional velocity, and since D is at rest with respect to the frame of reference, D would also have acquired that much velocity, and the acquired velocity is simply given by half a delta t square, which is equal to half a delta t is h square by c square. So by the time the photon emitted by the source S reaches D, it would have achieved I am sorry, I made a mistake over here. During the time delta t, the velocity achieved by the frame of reference is simply given by the additional velocity acquired by the frame of reference is simply given by a times this time difference delta t, which is equal to a h by c. So by the time the photon emitted by the source S reaches the detector D, the velocity of D would have increased by an amount equal to AH by C. So the velocity difference between the source when it emitted the photon at time t equal to t1 and that of the detector at the time it detects the photon or the photon reaches the detector is simply AH by C. Now in this case, D is moving towards S. So we have a situation that we considered earlier. The source and the detector are moving towards each other, and the relative velocity between the source and the detector is given by V equal to AH bar by C, because this is the extra velocity that the detector achieved over the velocity of S when it emitted the photon at the time it detects the photon emitted by S. So using the formula relating the frequencies of the observed photon and the emitted photon when the source and observer are moving towards each other, which is given by nu dash is equal to nu times square root of c plus b by c minus v, and substituting for v using this expression, we have nu dash, which is the frequency observed by the detector, is equal to nu times c plus ah by c, because v is equal to ah by c, divided by c minus ah by c. So this can be written as this factor nu times square root of, taking c as common, c square plus, or maybe taking c out as common, this is equal to c into 1 plus ah by c square divided by, in the numerator, the denominator, this is again 1 minus ah by c square. And cancelling the c, we get the expression nu dash equal to nu times square root of 1 plus ah by c square by 1 minus ah by c square. And since we have assumed that a is very small and all the velocities involved are also very small compared to the speed of light, and we know that ah by c is the velocity acquired during this small time, ah by c is much smaller than c, or in other words, ah by c square is much smaller than 1, and then we can expand this in the following way. We can write square root of 1 plus ah by c square as 1 plus ah by c square to the power half into 1 minus ah by c square. And expanding this will be 1 plus half times ah by c square plus higher order terms times, and over here this would be 1 minus half ah by c square plus higher order terms. Now multiplying, I will get 1 and 1 1. Now this half ah by c square, this appears with a minus sign, and therefore this will become plus. So 1, then this product gives half ah by c square, and this product gives another half ah by c square, and we will get 1 plus ah by c square plus higher order terms in 1 by c. So neglecting that, for ah by c square very small, we can approximate nu dash as nu times 1 plus ah by c square. Now, according to the equivalence principle, this frame, which is moving with a constant acceleration a, should be equivalent to a frame in a gravitational field acting in the opposite direction with the magnitude of acceleration equal to the acceleration due to gravity. So, this frame of reference, which is accelerating with an acceleration a in this direction, should be equivalent to a non-accelerating frame of reference in a gravity field with acceleration due to gravity acting downwards in this direction with g is equal to a. So in that case, ah by c square, this factor is equal to gh by c square, but gh is equal to the difference between the gravitational potential at S and the gravitational potential at D. So this is equal to del phi by c square, where this delta phi is equal to phi gravitational potential at S minus gravitational potential at D divided by c square. And therefore, this formula relating the frequencies in the frame S dash and in the frame nu can now be related as nu dash equal to approximately equal to nu times 1 plus gh by c square, but gh is equal to delta phi, the change in the gravitational potential. So nu dash is the frequency of the light observed by the detector, and nu is the frequency with which it is emitted at the source. Now we consider light emitted by the sun at frequency nu, and the gravitational potential at the surface of the sun is given by minus g m by r, where m is the mass of the sun and r is the radius of the sun, and g is the gravitational constant. And this light is observed at very large distance from the sun, for example on the earth. Now the gravitational potential energy has negligible magnitude far away from the sun compared to its value on the surface of the earth, surface of the sun. This is because the gravitational potential energy goes like 1 by r, and very far away from the sun, r will be very large, and therefore the gravitational potential energy would be negligible. So if we want to compute delta phi, which is phi on the surface of the sun from which the light is emitted, minus phi d. Now d is a detector, and we assume that we are observing this light from Earth. So let us say this is phi e. We see that phi e is almost 0 and phi s is equal to minus gm by r, the gravitational potential energy potential at the surface of the Earth, so at the surface of the Sun. So del phi is given by that. Then the frequency of light observed on Earth, which is nu dash, is approximated by nu, which is the frequency with which it is emitted on the surface of the Sun, times 1 plus delta phi, but delta phi is minus gm by r approximately, because phi on Earth is approximately 0. So this is nu times 1 minus gm by r by c square. And gm, r and c square are all positive numbers, and therefore this nu dash is nu times a number that is smaller than 1, and therefore nu dash is less than nu. So the frequency observed on Earth of light emitted from the Sun is less than the actual frequency with which it is emitted. So that means the frequencies, the observed frequencies, gets shifted towards the red region, to the lower wavelength, to the lower frequencies or larger wavelengths, and therefore this shift, this red shift in the frequencies, because of this gravitational potential energy, is called the gravitational redshift. As a second example, we consider the case of light observed from an accelerated frame of reference. We consider two frames of reference S and S dash, with S dash moving with an acceleration in this direction relative to S along say the y direction. So this is the y direction. At time t equal to 0, we assume that S and S dash coincide, S bar coincide, and a light is emitted at the x equal to 0 and x bar is equal to 0, y equal to y bar equal to 0, and at time t equal to t bar equal to 0 in the x direction. So light is emitted at the origin, and the origin of S and S bar coincides at time t equal to t bar equal to 0. So the clocks are also synchronized. So at that time, initially light is emitted in this direction. Now in the frame S, since light is emitted in the x direction, it will be moving along the x-axis. So the trajectory of the light is a straight line over here. Now, assuming that a is very small, and for very small t, the velocities involved are extremely small, and we approximate the transformation equation of the coordinates of an event between the two frames to be given by the non-relativistic transformation equation. So that is x bar is equal to x, and z bar is equal to z, and y bar is equal to y minus the distance between them. So now the frame of reference S bar would have traveled a distance equal to half at square in time t, and therefore we will have y bar equal to y minus half at square, and similarly t bar is equal to t. Now the trajectory of the photon in the S prime is then given by x bar is equal to, that is the x component is equal to c times t bar, and y, since it has moved in the direction y with over a distance of half at square, the y coordinate will be minus half at bar square. So in the frame S bar, the coordinates of the light or the coordinate of any event on the trajectory of the light is given by x bar is equal to ct bar and y bar is equal to minus half at bar square. Whereas in the frame S, x is equal to ct and y is equal to 0. So this is what get transformed to that. Since x bar is equal to x and x is equal to ct, and since t bar is equal to t, this is equal to ct bar, and y bar is equal to y minus half at square, but y is equal to 0 in the frame S because light is traveling along the x direction, so y is always 0 and x is equal to ct because it is traveling in the x direction. So now y is equal to 0, that means this is equal to minus half at square, and since t is equal to t bar, this is equal to minus half at bar square. So the coordinates of a light event corresponding to light emitted in the x direction in the frame of reference x is given by x bar is equal to ct bar and y bar is equal to minus half at bar square. And this trajectory is given by this picture, this green line. In the frame S, it is a straight line and is given by the straight line, green line. And in the frame S bar, x changes as ct bar, but y bar is equal to minus half at bar square. So this goes like this. So we see that the trajectory of light as seen from a uniformly accelerating frame of reference moving along the y-axis with acceleration a is in fact curved, whereas in the frame of reference S it is straight. But now we invoke the principle of equivalence, which says that it is impossible to distinguish whether between a frame of reference traveling with a uniform acceleration and the effect of gravitational field in a small enough region of space-time. So an observer in a gravitational field should experience the same thing as an observer in this accelerated frame of reference. So an observer in a gravitational field should observe the path of light as curved. Now, while discussing the Einstein equivalence principle, we have mentioned that we will be able to construct local inertial coordinate systems which will appear flat locally, that is in an infinitesimally small region of space-time around the point at which we construct this local inertial coordinate system. And in small enough region of space-time, the laws of physics should reduce to those of special relativity. But if we move away from this point, these inertial coordinate systems are no longer valid. So that means we have a situation corresponding to the space-time where we can construct local inertial coordinate systems which we cannot use globally, whereas in the case of special relativity we could construct global inertial coordinate systems, and the space-time there in special theory of relativity was found to be flat. But here we cannot construct a global coordinate system, but we can have local inertial coordinate systems. So the space-time is such that we can have local coordinate systems where it appears flat, but as we move away from that, these coordinate systems move away from that point, these coordinate systems are no longer applicable. So this corresponds to a curved space. And the mathematical structure of differentiable manifolds allowed a description of such a space. So we have to consider the space-time as a differentiable curved manifold.